Hi, I'm Kevin Zielnicki, a machine learning architect at Stitch Fix, and I'm going to talk today about the evolution of our approach to personalized fashion recommendations. So, in this talk, I'll start with some background and motivation about our business setting, then walk through some developments in our model architecture that have informed our current approach to personalized fashion recommendations. And finally, conclude with the impact that we've seen from recent updates that we've made. And hopefully through this, I'll share some takeaways that you may be able to apply to your own business domains. So first, I wanted to ground in the business setting of Stitch Fix. We were founded about 12 years ago and have been a public company since 2017. We provide personal styling services to nearly 4 million clients across men's, women's, kids, with a wide array of sizes and over 1,000 different brands. And at the core, what we do is we use a combination of expert stylists and data science to transform the way that people find what they love. So the way that this works from a client perspective is that a customer will sign up, fill out a personal style profile, which contains information about their preferences. Then they will schedule a fix, which is assembled for them by a stylist and contains typically 5 items that they will get to try on at home and keep the things that they like and send back the rest. And then when they do so, they can check out and provide feedback on the items, what they liked, what they didn't like. Our algorithms and stylists will use that information to continue to learn about their preferences and provide even more personalized options when they come back to schedule another order. And also through this process, we have a direct shopping feature called Freestyle that also updates along with their preferences and can offer another way to engage and shop for items outside of the fix cycle. So this client journey has multiple personalization and learning touch points where we get a lot of information about our clients' preferences and what they're looking for. So as soon as a client signs up, they fill out a profile that gives us a lot more information about them than most retailers will have about their clients, from things like sizing to demographics to particular questions around, for example, how often they dress up for various different occasions. And this gives us a starting point for understanding our clients. And then we also have a number of ways that they can update our understanding of their style or get us more in-depth information. So we get a lot of engagement with our Style Shuffle app, which allows customers to rate different items that they like or dislike, which we then boil down to a deeper understanding of their style preferences. And finally, when customers check out, they can fill in a number of attributes about the items that they either kept or didn't keep, and whether those items fit right, were too big, too small, match the kind of style that they're looking for, fit in the right budget. And we get a lot of engagement with this as well. So 85% of our checkouts leave us feedback about the items, which is a lot higher than most retailers because we have this ongoing style journey with our clients who we have a partnership with to help guide them to the things that they're looking for. So we then use that data in a wide array of different algorithms for filling in our personal styling recommendations. But at the sort of foundation of this and our longest running algorithm is our probability of sale algorithm. So this is an algorithm that attempts to predict for any pair of a client and an item whether a client will purchase that item. And it's based on data around observations of which items a client purchased and versus did not purchase. And this allows us to produce better predictions and better recommendations of items to clients. So this is a really important foundational model for us. And improvements to this estimation allow us to drive a better customer experience, leading to revenue lift and increased customer satisfaction. So continuing to develop and improve this algorithm is a core focus for our team. But as our business has evolved, we've seen an increase in complexity and a number of different ways that we've had to serve these recommendation models for probability of sale. So this has led us to, again, reconsider and evolve our modeling approach. So in particular, as we've increased the number of ways that clients can engage with us, they're interacting with new features like our direct buy freestyle option. We're serving these different product surfaces with different models that were tailored to those product surfaces, but didn't necessarily have a unified understanding across product surfaces of the client in a holistic sense. Additionally, as we were adding new models for different product services and different business groups, like men's and women's and kids and UK, we had to integrate new data sources, often with multiple different models, which required additional time investment to be able to enable improvements across different models. And finally, having different models serving these different recommendations increased the maintenance surface area that we had to keep track of. So this is more things for the team to maintain, more things that could potentially fail. And having this overhead is a drag on development velocity. So with that in mind, we had an opportunity to reconsider our modeling approach and develop a novel model architecture, which we called a client time series model. And so I'm going to spend a bit of time walking through some of the core principles that we incorporated into that model. I'm not going to go into the full in-depth technical details of this model. We have a lot more information about it on our multi-threaded tech blog, which I would recommend checking out if you want to do a deeper dive into this model. But here I'm going to focus on what I think of as some of the important foundational principles of this model and of our sort of change in approach from our previous models that I think can be some generalizable takeaways that can likely apply in other domains as well. Each of these three things I'm going to go in more depth and talk about what they mean, why these are important to our modeling approach, and how they might be applicable or in what settings they might be applicable for others. So to start with, we knew that we wanted to unify an array of different models that were perhaps modeling clients in different settings with a single holistic understanding of the client's state. So like many neural recommender system models, our approach relies on estimating and embedding representation for each user and each item, and using a dot product to predict outcomes, such as the probability of sale of an item. And with our growing array of models, we had multiple different models that would learn their own client representations and their own item representations, often based on shared data with each other, but separate training runs and separate embedding spaces. And so our first goal was that we knew we wanted to simplify this by learning a single embedding for each client, regardless of what prediction domain that we were making a prediction for them in. So to sort of visualize how this simplifies things for us, this took us from a many-to-many modeling setting where we had different data sources for information about our clients and different prediction domains, each of which had their own model that would interface with these client features. And then updates that we would make to features would have to sort of separately be promulgated to these different models. And this would introduce a fair amount of complexity and maintenance surface area, as I talked about earlier. Whereas by moving to the right side here, by having a centralized view of client state with a single client embedding that could then be used to make predictions that are domain specific into different domains, we're able to have this sort of act as a decoupling intermediary where we could separate the understanding of mapping client features to this client embedding representation from the problem of predicting outcomes in different domains from the client embedding. So this is fundamentally what allowed us to reduce the number of different models that we were having to serve and maintain. And so I think this type of multi-domain approach is a pretty useful one, probably in a lot of different areas as well. So this allowed us to share information across domains, but preserve the unique objective of each domain. Each domain can have its own target data, its own objective function. So for each of these things, I'm going to just briefly share where I think that considerations for where it might be useful. And in this case, I think that this type of approach is quite useful if you have multiple related types of recommendations that you need to serve that could benefit from sharing data across them that have some commonalities between them, but also have their own sort of unique attributes as well. Whereas this would be a lot less relevant if you only have one type of recommendation, or if you have different prediction domains that are so different that they really couldn't be well served by unification. So I think that this is fairly straightforward, but also for us a very powerfully simplifying approach. So next, another thing that was really core to our model is treating events as our universal abstraction for our client data. So this is a really important attribute of our new modeling approach, and also a pretty significant shift from how we were previously developing these models. So in our new approach, we model clients purely as a sequence of time-stamped events. In contrast to our previous models, which used either tabular data about client features such as their demographics and summaries of past purchasing and things like that, or sometimes a hybrid of tabular and event data. In contrast to that, we have moved to something that is purely based on a sequence of events of client interactions of various types. So modeling event data directly does add some complexity compared to tabular data, and changes the type of modeling approaches that you can use. So a lot of the things that kind of make sense in a traditional tabular data world are not really applicable to directly working with event data. But we do get a lot of benefits from making this shift. So first of all, event data is really central to real-time distributed data processing. In an engineering sense, this is like event logs are really at the heart of data processing systems. This is like the key insight that led to Kafka and other distributed event processing systems. So by moving to event data, we're able to take advantage of a lot of those sort of distributed data processing best practices. Also, event sequences that have been, there's been a lot of progress in recent years in establishing state-of-the-art model techniques that work well with event sequences. Most famously, transformers. And we use a transformer style architecture in our approach, which I'm not going to go into detail about here. You can read more about that on our tech blog. But we found that these approaches make working with event sequences something that is feasible to do. And then finally, focusing on event data gives us a number of modeling benefits. And I'm going to go into more detail on those in this next slide. So the things that I see as the main benefits of the event abstraction for us is first, that we get a full temporal context. So we know kind of intuitively that the timing of events is relevant. For example, in our setting, jeans that a customer bought just yesterday are going to have a different meaning for what they're looking for, different implications for their preferences than a blouse that they bought a year ago. And by treating all of these purchases as events, rather than trying to sort of aggregate them into a derived tabular feature, gives us a much more nuanced way to understand the implication of those for our customers' current preferences. And then also, this allows us to sort of better handle the evolution of customer preferences over time. So the state of a client and the state of somebody's preferences aren't a static thing that we gradually learn about, but rather something that itself evolves in time. So people's style changes over the years, fashion itself changes over the years. And by having everything associated with a timestamp, we can do a better job of handling preference evolution over time. And then, and I think this is a really important one for model development, and helps us avoid a lot of bugs, is that this approach allows us to have a model that's time safe by design. And so what I mean by this is that by associating timestamps with all of our observations, we can ensure that we're not accidentally using data about the future to predict things about the past. Which is obviously something you never intend to do, but anybody who's worked with predictive modeling will know it's quite easy to introduce bugs where you accidentally have some summary feature that uses information in a way that kind of accidentally leaks information back in time and makes things look great in backtesting metrics, but doesn't actually hold up under any scrutiny or generalize to actual effectiveness of a model. And so by having everything associated with timestamps, we can pretty cleanly eliminate the possibility of using information from the future to predict things about the past. And then by having events as our single abstraction and treating every observation as event, we can simplify and standardize interfaces and ETLs compared to if we were trying to do a hybrid approach of having a combination of event and tabular data. And this helps us keep us handle on some of the kind of intrinsic complexity of working with event data. And then finally, the event approach gives us flexibility to serve real-time use cases effectively and efficiently. So for example, we can do a batch compute during training to compute client state up to a high watermark timestamp, and then in production at inference time, only update that with new events that have just arrived after that timestamp. This gives us sort of a seamless transition between batch cases and real-time cases, and I think it has helped us to be able to handle real-time use cases more efficiently and more safely. So where I think this can be useful, and I think that this event view is a very powerful one, and I think it is a very generally applicable one. I think that really, if you think about it, all prediction tasks are really event-based, whether we think about them in that framing or not. So I think that anytime that you're doing a predictive recommender system, you could frame it as an event-based problem. But it does introduce some more complexity to do this, often compared to a simpler tabular feature-based model. So while I think it is a nice framing, it's not necessarily the go-to for every potential use case. But I think it is seriously worth considering if you have some sequence of interactions over time. You want to learn from them over time. You want to make sure you're doing that in a time-safe manner. But I think that it's okay to not use this if the additional complexity doesn't really pencil out of having an event-based model. And maybe often it's a starting point to go with a sort of a simpler featureized tabular approach, and then see if adding the complexity here justifies itself. But in our case, it definitely was worth the shift. And the third principle I want to talk about is a specific way that we handle events, which is a split between updates and targets. So what I mean by this, in contrast to a typical sequence model, where we just have a sequence of events, here I'm defining two types of events, which we decouple from each other, which are observed updates and prediction targets based on a time of observation for the update or a time of prediction for the target. And this gives us a flexibility to define separate schemas for separate types of updates and targets, and also is really critical to our time safety strategy of ensuring that that if there's a delay between when a prediction is made and when it's observed, that the proper data is being used for the time of prediction, and we don't have a sort of a violation of time leakage. So what do I mean by updates and targets? I think to make that a little bit more explicit, what I'm defining as an update event is some piece of observation of information that changes our knowledge about the client state. So for example, in our setting, this could be something that they filled in the onboarding survey. It could be feedback that they left during fixed checkout. And whatever it is, it's going to have a timestamp associated with when that information is received by our systems. So like the time of checkout, the time of filling out that survey. And this is analogous to in a tabular model or regression model, the features or X. So it's the things that we're using to update our understanding of the client, the inputs to that client state. Whereas targets are also treated as events, but these are outcomes of interest that we're trying to estimate as a function of the client state that we are producing from the sequence of updates. So for example, this is something like the probability of sale of an item that we need to estimate. And so targets have a timestamp that is associated with when the prediction needs to be made, when it's used. So for example, the time of styling in the case of when we're making a prediction about whether the customer will purchase something or not, and serving that to our stylists. This timestamp is encapsulates when we need to be able to make that prediction, and thus like what information is available to us at that time. And this is analogous to the target in a tabular model or regression model. It has to be associated with a loss function. We can have different types of targets with different loss functions. That gets back to our sort of multi-target nature of the model from the unified client embedding section. But whatever type of target it is, it has to have a loss function associated with that type. And targets, importantly, don't affect the client embedding directly. They're not things that we need to take into impact the client embedding. They do directly affect it by influencing network weights, but they're not used as inputs. So having that separation between these two types of events is, again, really essential for us for ensuring time safety, in particular because we have a lot of events that are observed after some perhaps significant delay. For example, checkout takes a lot of time from when the items are initially picked out versus when the customer eventually decides whether to buy them or not. And we might have to make other predictions in that time. So having this separate types of events is useful for keeping a handle on that and ensuring that we're using the right things for the right time. And I think it's generally useful in any sort of similar setting where outcomes might not be measured for a while until after another prediction is made. I think also this split can be useful if you're dealing with this kind of multi-input, multi-target setting, because it's a nice way to be able to define different event schemas and the kind of event schemas that you want to define for update information might be quite different from the things that you need to define for target information. So treating both of these things as events, but treating them as two different types of events gives us a clean way to handle that. On the other hand, you might not need this if you have a simpler setting where outcomes are associated with predictions that are observed before any additional predictions need to be made, or if you don't have a large number of different types of events or targets. So in a sort of typical sequence model, in the kind of simplest case of, say, like a sequence of text, like in a large language model, this type of split is probably not really necessary. But in our case, and particularly dealing with the timestamps of these things, this is a very useful separation for us. So I hope that some of those takeaways are useful and to your approaches as well. For us, the model that we built out of all of these things is something that we've been pretty excited by and has delivered some pretty significant benefits for us. So we've done extensive testing and rolling this out over the last year. And I've seen significant benefits in four main areas. So first of all, in terms of business outcomes, in an A/B test, we measured 1 to 10% improvements across the board on virtually all of our KPIs, including improvements to revenue, retention, client satisfaction, various engagement metrics, and so on. We also simplified things a lot from an engineering perspective. So we saw a significant reduction in compute resource consumption due to a reduction in the number of models trained by consolidating things into a single model. Also, we have a lot lower maintenance service area. So due to this model consolidation, there are fewer things that we need to maintain and less overhead for the team there to keep everything running. And finally, we've seen improvements in terms of our development velocity. So by having a unified framework, we're able to make improvements to one core model and then get the benefit of those improvements across a variety of domains. And so this has allowed us to make model improvements faster and more broadly than we were able to in the past, and realize the benefit of those. So again, we've been very happy with this approach, and I hope that some of the things that we've learned from this are takeaways that can be used in other areas as well. And again, I recommend checking out our multi-threaded tech blog if you want to learn some more about the details of this model. Thank you.